this is going to be the last video on this talk. So earlier we discussed the motivation and background of the index with constraint. We also developed an abstract formulation to relate the index with constraint and a general index. Then we applied that abstract formulation to characterize type 1 and type 2 more index for capillary surfaces. So in this last part of the talk, we're gonna discuss some index estimate. So there are also application of the abstract formulation we described earlier, but is a little bit more involved. In order to state our theorem, let me introduce a new definition. So let mi1 plus 2 sigma here be the corresponding Moore index subject to type 1 and type 2 constraint. So as we discussed earlier, for the partitioning of a convex body, there are different constraints we can consider. We can consider these constraints separately, or we could consider them together. So here we consider them together. And the main theorem had two parts. The first part here characterizes the case when the index here equal to 0, so the stable case. Then if the index here equal to 0, then sigma here must be umbilical. That is, must be spherical or flat. Otherwise, the index is going to be greater than or equal to some number L, and L here is totally determined by the geometry of sigma. So this theorem can be useful in the theory of capillary surfaces as follows. So we can consider some concrete capillary surface, and then the geometry of this surface is determined. Then we can use this geometry to determine the number L, and then immediately we know that the index for this concrete example must be greater than or equal to L. Also, another feature of this theorem is that this is here we give a lower bound for the index, but it is the lower bound here comes from the geometry of the hypersurface. So as I said earlier, the index theory is a very, very popular topic in geometry analysis. So there are numerous lower bounds for the index of certain operator associated with some optimization problem. However, many of these indices actually determined by the topology of the hypersurface. That is, using the topology of the hypersurface, we can construct some information that decrease the function of the second order. However, in comparison, our theorem here gives the lower bound depending on the geometry of the surface and independent of the topology. So I think that's why this theorem will be very useful in the general theory of capillary surfaces. So here are some immediate observations. First of all, it is clear that the type 1 plus 2 index is no greater than the type 1 or type 2 index. So the type 1 plus 2 index considers the operator in a smaller in the intersection of these two subspaces. So the index here must be no greater than the index of the type 1 and type 2. So that's why the lower bound for the type 1 plus 2 index is also the lower bound for the type 1 or type 2 index. So that's why this theorem is the most general, is stated in the most general form. Another observation is that the first part here recovers the results of Wang shear and Zhao shear as special cases. So this group of mathematicians, they study either type 1 or type 2 stability case and obtain some characterization. We can recover the results as special cases of our main theorem here. And the next observation is that the second part suggests an index jump, and this is not surprising because we see a lot of index jump when consider minimals and constant mean curvature surfaces. So this is just another indicator of this behavior. Also, the last but not least observation is that this is sharp, and it is sharp in the following way. We consider a family of cylinder of radius r inside the ball of the unit ball, the unit Euclidean ball, and here we let r vary between 0 and 1. So the observation is that, so here we have a concrete capillary surface with a lot of symmetry, rotational symmetry. So all the PD mentioned earlier can be reduced to system of ODE, and we can understand this system of ODE and then make conclusion about the corresponding PD and the conclusion about the corresponding geometrical implication. So that's why we can compute the index for these concrete examples precisely. The summary is that as R varies from 0 to 1, the index varies from n plus 1 to infinity. So clearly there's some index jump because the index doesn't assume any value between 0 and 1, but it's a start at n plus 1. And also there is an interval such that if the radius is inside the interval, then the index is exactly equal to n plus 1, and the number L here is also equal to n plus 1. So for these cases, the inequality, the index estimate, actually becomes an equality. So that's why the index estimate is sharp in that sense. So now let me discuss some open problems in this direction. The first problem here is very, very accessible to graduate students. So instead of the ball, we can consider convex body symmetrical certain symmetry in a Euclidean space. And then we ask the question of finding all stable capillary surfaces in these convex bodies. It is expected that because of the rotational symmetry of the convex body, many of the PD consideration can be reduced to some ODE consideration, and that's why it is possible to characterize the stable case for this situation. And ODE is certainly a subject suitable for graduate students. So this problem is very accessible to graduate students. Now the second problem is a little bit more sophisticated. Can we replace L by n plus 1? And we saw from the example here, the index starts at n plus 1 and it goes to infinity. It jumps, it doesn't assume any value between 0 and n. And L actually can be equal to n plus 1 for certain cases. So that's why it is natural to ask whether we can replace L by a constant only depending on the dimension of the hypersurface. And this problem is difficult. I don't know how to do it. The third problem here is about index with multiple constraints. So we had abstract formulation for index with one constraint, and we can apply this theorem repeatedly to obtain a version for index with multiple constraints. However, in order to do that, we need to verify that nice assumption at multiple levels. At one level, the nice assumption is equivalent to the Fresnel alternative. At multiple levels, I don't know what is the equivalent to. So that's why it is still interesting to study the index with multiple constraints and determine exactly how it is related to the general index. So that's it for my talk, and I thank you very much for your attention. If you have any questions, feel free to let me know one way or another.